In order to collect data for current of the water, what you'll need is you'll need your tape measure, you'll need a stop clock, and you'll need a variety of oranges. As you can see, Mr. Matthew down there has an orange. And we stretch the tape out 100 feet. And with the stop clock, I'm going to signal to Mr. Matthew to go ahead, or he's going to let me know when he puts it in the water. And I'm going to start my stop clock. As soon as he does that, and we're going to let the current carry the orange down to me and get a timing on how long it takes for that orange to travel that 100 feet. Are you ready, Mr. Matthew?
I'm ready.
Okay, I'm ready too. Let me know when you're ready.
Okay, make sure you get it right even with the end of the tape. And
all right.
Ready, go.
Okay, now I've started the stop clock, and I'm going to wait until the orange reaches me, and then I'll stop it. And I'll repeat this procedure 3 times to get my data, so I have an average amount of time it takes for that orange to travel the length of 100 feet in our river. Okay, stop. 9 minutes and 40 seconds was the length of time it took the orange to travel 100 feet. I'm going to repeat this 2 more times so you can see the current's not flowing real fast. If we just had a rain or something, it'd be going much swifter. But right now in the middle of the summer, when we're collecting this data, it's moving pretty slow. So you can see if you have to collect this 3 times, it may take you upwards of a half an hour to collect all 3 sets of data. You'll then average the time and use that to figure out the speed of the stream in miles per hour, doing a little bit of mathematical tinkering back in the lab. Make sure one of your lab partners has their journal so they can record down all 3 sets of times that it took the orange to travel 100 feet. The reason why we use an orange and not a block of wood or a tin can or anything like that is it's pretty organic, and it may travel all the way down the river, and somebody might see that orange and know that you're part of the River Watch program and you're collecting data on the West Fork of the North Branch of the Chicago River. So that's all there is to collecting data for current.
We're going to take the raw data you collected from stream velocity and turn it into a standard number that's usable by ourselves and by other people looking at Chicago River water data. Your team has the job of taking physical features of the river, velocity, discharge, and weather, and seeing how that affects the quality of the river itself and the wildlife that lives around the river. So you have a pretty vital job to do here. You remember outside that you took the orange and let it travel for 100 feet, and you should have done that 3 times. And as you did that, you measured how much time it took. Now the example I'm going to show you here for our 100 feet took 9 minutes and 50 seconds. Now that data is fine, but the standard that we use is in meters per 1 second, so we've got to do some converting here. 100 feet equals 30.77 meters. You can double check that if you want, but just trust me. 9 minutes and 50 seconds translates into 590 seconds. So I've got meters per 590. I now need to do some division. And the way you're going to do that is divide the distance, meters, by the time, 30.77 over 590. It's going to give you a figure of 0.052 meters per second. The orange travels 0.052 meters in 1 second, 5 centimeters in 1 second. Not very fast, and that may have some meaning for you. You can see that if we did this in miles per hour, the number would be so small it would be meaningless to you. So this is a number you can picture in your head. So take this sample along with the other 2 that you took, make an average, and you have a nice reliable piece of data for stream velocity.
Once you've completed measuring how long it takes for the orange to travel 100 feet, your next step, you're going to have to get your waders on, your goggles and gloves for this step, and you're going to have to get into the water and measure the average depth across. What we're going to try and determine is the discharge of the stream. In other words, how much water passes by in a certain amount of time. You're going to need the current information that you just collected, and you're also going to need to make a stream profile. one of the things you need to take into consideration is the stream bottom. In this case, we kind of have a mucky, sandy bottom, and you'll give that information to your person that's standing on shore with their journal and tell them what kind of bottom that your water is traveling over. And then with the help of an assistant, what you'll want to do is you'll have a rope strung across the stream, and every half meter you're going to want to collect the depth of the stream from the surface all the way till it hits the substrate or the bottom of the stream. So the first thing I'm going to look at is I'm going to find my mark, which is approximately a half a meter away. And my lab partner, Mr. Matthew, will come by, and I'll make sure that I'm right on the right spot, and he'll measure the depth of the stream.
We've got 24 centimeters right there.
24 centimeters. And now I will move 1/2 meter away from that, and I will collect my next depth. My next depth for the profile of the stream from the surface of the water to the substrate is?
We have 29 centimeters.
Okay, 29 centimeters. We're going to continue this process all the way across the width of the stream. And there are plenty of places on this particular stream that we shouldn't have a problem determining the depth, because it's really not that deep of a river. You recall that when we were out at the river site collecting discharge data, what we did was we strung the string across the river and measured approximately every half of a meter what the depth of the stream was. And we continued to collect that data until we had gone completely across the stream. When you come back from the lab or from the river and then you're in the lab, you want to calculate the discharge. In other words, how much water flows by the stream in a given amount of time. In the case that we're looking at, we want to find out the cubic meters of water that flow by the stream per second. In order to do that, you just have to follow a real simple formula that is outlined in your stat manual along with this same example that I'm showing you. In other words, what they did was they measured from distance, the first distance from the shoreline to 1/2 meter out, and they measured the depth of the stream. In that particular case, it was 0.22 meters, okay? And they multiplied that 0.5 times 0.22, and they got the area of the stream for that one section at 0.11 square meters, okay? They continued to do this for every single section as they moved across the river. Since, as you recall, our river was about 9.5 meters in width, you're going to have approximately 19 sections that you're going to do this for. Each time you will take the 0.5 times the depth and get your area. When you get done with this, you're going to total up the entire areas of all the sections of the stream so that you get a total area for the stream all the way across it. Once you have that total area, you're going to do the exact same with another segment of the stream that you took. In other words, you're going to take two cross sections of the stream. So you're going to have quite a bit of data to manipulate. When you do that, you add the two together, the two averages together, and divide by 2 to find the average cross-sectional area of the river. In this particular case, in your example, when they averaged these out, it came to 2.83 meters squared. So they were working with a relatively small stream. Now to calculate discharge, all that you have to do is take your answer from the velocity that Mr. Matthew told you how to find times the average cross-sectional area. And that will end up giving you the meters cubed per second. So it's a very simple mathematical tinkering. The only thing that you have to do is you'll have a large series of numbers to work with. But once you get that, and you only have to do this once, you'll have two different stream widths, and you'll average them together and divide by your average stream velocity, or multiply by your average stream velocity, and then you will have the discharge in cubic meters per second.